The second part of this lesson deals with the limit rules. For normal students, this is going to be a very, very short section because the latter half of this video, or latter 3/4 as a matter of fact, will be devoted completely toward mathematics majors. For them, it is going to be important. For others, not really. You'll see what I mean when I get there. Okay, here is a summary of limit rules that we have to remember. First, the trivial limit rules. Trivial limit rules. A constant k remains as constant k no matter what. The second rule is equally as trivial. X approaches to c, then, of course, x approaches to c. That's all there is. Trivial. The other rules require a little bit of thinking, but again, they fit our common sense beautifully. Limit of sum is the sum of the limit. Limit of coefficient times a function is coefficient times the limit. Limit of the product is product of the limit. Limit of the quotient is quotient of the limit. Of course, denominator should not be 0, and that should be reflected. Otherwise, the only condition we have to impose for all these is that the limit must exist. Here's very, very trivial example. Let's do this computation. Limit as x is approaching to 1, 3x plus 2. How do I find out? First, let's use the addition rule to separate the 3x part and the 2 part. And then use coefficient rules to get 3 out. And then we use the trivial limit rule. X is approaching to 1, so x is 1. And this is constant plus 2. So we have 3 plus 2, that's 5. Of course, nobody does computation like this. Everybody will be able to see that you can plug in x equals to 1 directly here. So why do we fuss about all these limit rules? The reason is a little bit theoretical. The limit rules allow us to plug in. So if we do not discuss limit rule, then we cannot actually plug in either. But after discussing those limit rules, yes, we can. So plugging in the values should be the very first thing you should do in any limit computation problem. Plug in, and if you get a value, that's going to be it. If you end up with something like 0 over 0 or 0 times 0, now you need some further work, and that's going to be the topic for section 3. The remainder of this section 2 will be devoted mostly upon mathematics majors here. Some further things like composite function rule. If you have a known continuous function, then limit simply goes in there. But typical rules are kind of like this. If you have a radical or square root mostly, you can just put those limit inside. Exponential of limit is, limit of exponential is exponential of limit. You can do the same thing for a lot of other functions, log function, trigonometric functions, and so on, as long as you're considering all these within the domain of those functions, of course. Another thing that you have to remember, again, this is getting a little bit theoretical. If f is less than or equal to g around a certain x value, then clearly the limit has to be less than or equal to the limit of g. Well, those are local properties, so locally if f is less than g, then the same has to be reflected on the limit. That's pretty easy to understand. The sandwich rule, on the other hand, requires a little bit more thinking, and this is an application of this inequality rule here. If f is less than or if f is greater than or equal to g1 but less than or equal to g2, and then g1 and g2 give you the same limit, then f is squeezed by these two and then generate the same limit value. The proof is very, very simple. All we have to do is apply this inequality rule 2.7 twice. Because f is greater than or equal to g1, limit of f is greater than or equal to that of g1, And same here, f is less than or equal to g2, so limit of f has to be less than or equal to g2. But what did he say? g1 and g2 have the same limit. So what kind of function, what kind of limit, or what kind of real number is both greater than or equal to L and less than or equal to L? Well, that's how we get the limit. If you're not convinced with your proof, or if you're a little bit uncomfortable with this, then this kind of visualization will help. Here's an example of this sandwich rule in action as a visualization. We have badly behaving function here, x squared times sine of 1 over x. This graph is really badly behaving. However, because sine function is captured between -1 and +1, sine is always between -1 and +1, isn't it? So this x squared times sine of 1 over x has to be in between -x squared and +x squared. And what about those limits? They are both 0. Consequently, the limit of this badly behaving function has to be 0 as well. And this picture says it all. Y equals x squared, the top parabola. Y equals to -x squared, the bottom parabola. And they all converge to the same y-coordinate value, both left-hand side and right-hand side. So squeezed by these parabolae, top and bottom, this badly fluctuating function has to have the same y-coordinate value, L equal to 0 as the limit.